Now, I think Danish and some other people already know him very well. He has worked with Injuma, and then we have worked in NLC, Beijing, and now he's working with Technion with me, the postdoc, and he's interested in this one. He's actually mapping and cross correlation basically with radio galaxy effects to explore Sunyaev-Zel temperature now.
Yeah, thank you. Thank you. My name is Ariel Dujikwe. I'm introduced, and basically today I want to talk on the cross correlation of TSE and neutral hydrogen intensity mapping from FAST, and uniquely combine the advantage of this probe theoretically to see what constraint we can obtain on the error of the H1. And then what is the next that we want to do from here when the time arrives. To say a bit more again about the SE effect, which a number of us know, is the inverse quantum scattering of the CMB photons by the hot gas in the galaxy clusters, and it's proportional to the property of the ionized baryon density and temperature. And this effect results into characteristic distortion in the CMB. And so with the TSE, we can study this distribution and physical properties of this ionized baryon, and which is informative to aid our understanding of the large-scale structure and the process of cluster formation and evolution. And the TSE are combined with different probes and used in different analyses. And I just show a few of the papers before going to what we've done before with Dennis and Wendy. We've combined the TSE with ISW to show that gas is correlated on larger scale, and also with the projected galaxy density field constructed from data using the wide field inference of the Explorer to place constraint on the hydrostatic mass bias parameter and constraint of the galaxy problem. And uniquely here, we're combining the TSE with 21 centimeter, and because hydrogen is abundant in nature, I mean, it's distinguishable from other emission line, and the observing frequency is a good measurement of the redshift of emission, and the neutral hydrogen intensity, which is different from this is different, of course, from cataloging the individual galaxies. So here, with the neutral hydrogen, we can have a direct emission from all the multiple galaxies, and then we have to advantage large sky coverage, and also have information of faint on the substructures. And people use this way until we're able to have enough information from the individual galaxies. And a number of experiments. I mean, it's ongoing to give us this information. We have omitted, this is IRAX from UKZ, operated by UKZ reference on PhD. We have the TN line, which escaped by itself, really fast here in China. And MICAT is also doing the same thing. And a number of studies in particular have given us information on the omega H1. We can make a direct measurement of the omega H1 at low redshift, and people do this by calculating the amount of gas in the galaxy. Basically, we determine the H1 mass function, which is similar to the stellar mass function, but in this case, the focus is on the neutral hydrogen content. And at about redshift 0.2, around that scale, an indirect measurement of the neutral hydrogen cosmic abundance is also possible using H1 spectral stacking. I could also always interested in that topic. And other methods like C2 to H1 conversion factor and also the DLA observations. But I work light in the category of theory and simulation, and in particular, we're interested to place constraint on the error of the uncertainties of the H1. So among the interesting topic, I narrowed down into these two, which it seems that I'm biased because the writer of these two papers are from the NLC. Fourier combined used the 301 data set to simulate the CSS galaxy survey and H1 density mapping for fast, and showed that it's possible to obtain with good precision the total H1 abundance with a relative error of 0.6. And then following after that, you were published a paper to combine using multi-dark n-body simulation to simulate the CSS spectroscopic galaxy data, and we tried from that. And also show that you can constrain the product of the omega H1, the H1 bias, and the galaxy hydrogen correlation coefficient to to good precision. However, the cross correlation involved is sensitive to relatively less massive EOs, and which points to one of the major goals of this work, and the fact that the unique advantage of combining the TSZ and the H1 is that in the 1 milliton regime, you can place constraint on the omega H1 and also the profile of galaxy helos and group. And we can do this if we treat the H1 in 2 different ways. We may decide to assume that the H1 is distributed within each dark matter following the density profile, and then a kind of averaging over all the H1 average galaxies, and we treat the H1 distribution this way, or we consider the H1 in discrete galaxy within the halo. That we consider the distribution in the satellite of the central galaxies. But for the work we're interested in, particularly if you're interested in scales above individual galaxies, then the former is sufficient. And basically, we could write down the density profile, and then from there it goes into the 2D Fourier transform of the temperature fluctuation field, which takes in as a recipe the Fourier transform of the normalized H1 low density profile. On the other we can write the 2D Fourier transform of the TSZ field, and all of this goes into recipe to calculate the 1 milliton and 2 milliton of the H1 auto, the TSZ auto, and the H1 TSZ cross path spectrum. One of the things that is important is that we have to be careful now we model the H1 mass. The H1 mass relation, using the Planck-Harman relation, we realize that it's sensitive to relatively smaller helos. But for the cross correlation that we're interested in, which is sensitive to more relative larger helos, the Planck-Harman relation is not sufficient. So we look to the Paglia relation, which provides 3 scales. The first scale basically assumes that the H1 fraction is consistent across all helos, but falls within this mass range. And the second scale also assumes that the H1 fraction decreases steadily with increasing helo mass, and for the extremely large helo mass, the neutral halo content goes to 0. But for the third spin, it follows as the second spin. But for the fact that for extremely large halos, you still have some neutral hydrogen content. So we use the Paglia relation to model the H1 relation in this project. And then for the RFI, how do we treat that in this theoretical forecast? We know from the temperature space the H1 brightness temperature, but we expect the RFI at this frequency domain for fast. And so we flag that out theoretically by looking at the frequency domain before and after this contamination region, and we only take into account the calculations from the statement. And for the noise and the foreground, using the fast survey parameter, we can calculate the fast, the terminal noise of fast, which is modeled as a Gaussian-wide noise. And we can calculate the variance using the NLXY, where the X and the Y are 2 different observables. And if we follow the foreground avoidance method, then we obtain the angular power spectrum of the cross correlation in units of Kelvin. And basically, if I say 3 things here, the cosmic variance dominates on small scale as expected because there is a limited number of independent modes in the observed volume of the universe. And As we go from the low Earth to high Earth, the short noise and instrumental noise becomes dominant over the cosmic variance. And the second low time, of course, contributes about 75% to the total observed power spectrum. And what we see in the little rise there is because of the smoothing canal. So here I show the mass dependence and the redshift dependence of the auto and cross correlation. And from the left, we see that the TSZ is sensitive to relatively massive low redshift object. And for the scale of L equal to 10, we would expect that the TSZ is tightly correlated with the fast, as the object is sensitive to redshift range that is also, fast redshift range is 0 to 0.35. And to the right, we uniquely point and see that 1 electron of cross correlation is sensitive to relatively larger object, which is a unique advantage of a cross correlation of combining these two probes. And with that, you can make a constraint on the error of this parameter, the profile, the galaxy clusters, and the omega H1, which we just multiply by H here. Uniquely, we see that the error here is smaller than previous calculation and measurement. Of course, this is calculation. And that would basically be because we are assuming a larger sky coverage here and not the observation time. And here we compare the result from the constraint on the UPP parameter, the vapor pressure profile parameter, with other work done before. Of course, we don't expect something tighter than other constraint, but something within the range of literature. And so we want to say that the story is not complete, indeed, because we want to then test for possible systematics, those due to RFI flagging in reality, the noise effect in the foreground is surveyable in a simulated. One other idea that jumps to mind is instead of doing H1 TSZ cross correlation using member simulation, one would combine the H1, the TSZ, and the galaxy probe together in 6.2 cross correlation to achieve tighter constraint and break degeneracy between the omega H1 parameter and other parameters. And yeah, if you have time, you can have a look at the paper, and contributions are welcome. Thank you for listening.